In this final video in the transport and fate unit, we're going to go through some review of breakthrough curves and plumes and also talk about some different variations, and then I'll go through the transport and fate homework. So the first thing is with biodegradation. If we have a breakthrough curve that looks like that, biodegradation is actually going to eat up the chemical. So it's not going to get all the way to the top. In fact, it might even get to a steady state. Some of the Domenica models we're going to use in the homework assume that. So it might just start to come up and then level off. And it might get to a steady state. That is, the chemicals getting eaten up just as fast as it's coming to the source. So this is with biodegradation, and the red is without biodegradation. Kind of similar for the non-equilibrium absorption. So if we have that for a breakthrough curve, or for continuous, or this for a pulse, with non-equilibrium adsorption, it'd actually take time to get up there, so it will kind of slowly approach that. Or in this one, it might come in and then tail off. So it's never getting down there. And actually, I could have a long tail to it. This is also becomes because heterogeneity. So really in pumping, this comes out more when you're pumping and trying to remediate something, because the water and the whatever you put in there is going through the places it can easily get to, and a lot of the chemical is stuck in places it can't get to very easily, so it slowly comes out of there. So it's really looks like non-equilibrium. And so actually I did my whole PhD thesis on that. But you never quite have equilibrium, and in a real situation, because it's just the variation in the subsurface, it's going to look a whole lot like non-equilibrium. And actually, don't want to get off topic here, but if I stop pumping, this concentration will actually come up because it's sitting there, and I start pumping again, it goes back down. If I have a preferential pathway, so I have, maybe I'll draw it over here. I have my aquifer here, and I have my chemical going through it. If it has a crack in it, well, the chemical will shoot through that crack. So you expect a nice breakthrough curve. So if I have that fracture there, it might just shoot through there real fast and then kind of slowly approach the top. So it short circuits the whole thing there. So the breakthrough curve will look very different. I ran into a weird thing way back in my master's thesis where we had this chemical, this dirhodamine WT, and it had these weird breakthrough curves. And what it actually was two different isomers. So one isomer that came through here and one isomer that came through here, and we put them together, we got this like that. So it took us a while to figure that out. So if you have like a double breakthrough curve, you're actually measuring two chemicals. That doesn't come up a whole lot, and by now we've kind of worked out which chemicals like xylenes that have isomers. But just another weird little thing that can happen. Rare, but it could happen. Summation notes for breakthrough curves. Remember, for a continuous one, we get the C or C0 equals 0.5 at where the centroid would come out. So that would equal to the retardation factor. So these are just copied from the examples we did. Breakthrough curves, we had two types: continuous injection versus a pulse or slug source. And we saw the differences there. Note that they spread out a little more, the more retarded they are, and the lower peak, the more retarded they are. Also, didn't really emphasize this, but we can plot these versus time or the volume. So if we know how much volume it takes in our aquifer, how much volume of water that is, we could plot this at the volume pumped through over the pore volume. It comes out the same thing. And actually, this would be T over the time for one pore volume, which is like a hydraulic retention time. So just put that in the back of your head there. And remember, we had, I did concentration versus time. We could also do concentration versus distance, where you have high at the source and then going down as you go out. And finally, nothing ever looks exactly like the ideal. But these are good things to understand. On the plumes, remember the centroid of the plume is at a distance of the groundwater travel divided by the retardation factor. So we did this example for a conservative, non-retarded plume. It got there at 800 days. So the retarded one is going to be halfway there, 800 days, if it's retarded with a retardation factor of 2. This plume spread out more with time and distance. I kind of did okay with the red one there. This is copied there. So the farther we go, the more it spreads out. It spreads out more in the lengthwise than it does wide. So this is one of those field studies that we have up above in our notes. And notice the other field studies, these were fatter plumes. So it's not exactly the same, but always it spreads out more in the longitudinal direction, the direction it's going, that it does side to side. For continuous plume, we get C equals C0 at about 0.5 at the distance the groundwater travels. So that's kind of where the centroid of the plume is. That's, again, assuming there's no biodegradation. So in this example, we had a retardation factor of 2. If there had been no retardation, the centroid would have gotten out there. So we would put a 5 milligram per liter, or C0 equals 0.5 there. Retardation factor of 2, it's half there. And then this again is be a plot of the concentration versus distance. And again, nothing looks exactly like the ideal. Let's talk through the transport and fate homework. As I record this, I have not had anyone hand it in yet. And so I'm going to go through it as it is now. If I have to make some modifications of it, I might modify this video, or I might just leave some notes there at Blackboard with you. So I have 6 problems. 2 we model with these Excel models. The first one is Quick Domenico. The second one is BioScreen 4, which is based on the same model. And then a problem just like in our examples on biodegradation, and then a couple on identifying breakthrough curves or drawing breakthrough curves, and then interpreting a plume and calculating properties coming from that. So this first one, I just drew this plume here as an example of what it looks like. We have a source area of 20 feet and a depth of 20 feet of the source area, and the initial concentration is 10 milligrams per liter, and we want to model it as being 10 years from the release. So obtain the Quick Domenico spreadsheet model. I put a link there. If that link's dead, you can just Google that and you come up with it. It's all over the place. We're looking at benzene, which is actually in the model as a default. It's usually the chemical of concern. And you have a site boundary 700 feet away that you're concerned with. You're going to model a plume of 700 feet. So we have data on the aquifer with fraction organic content, bulk density. So you're going to enter that in there, and it will calculate a retardation factor. Information on benzene. And then what we're going to do is we're going to fit the rate coefficient to the data. So we're going to put the data that we have in there. We don't have the rate coefficient yet. Everything else, we should be able to just plug in the numbers, and then we can put this data in there, and we want to model it and change the rate coefficient by trial and error and see if we can hit that. So I'll bring up the model here. So you can see what it looks like here. Again, you can plug all these numbers in here. It will calculate the retardation factor, and it will calculate the velocity. So back on the homework here, it says, what is the velocity of the retarded benzene? It calculates that. You're going to have to use the numbers to calculate the specific discharge and the seepage or travel velocity of the water, which are steps to get to the velocity of the benzene. And then you're looking at the boundary. What did we say? 700 feet. I'll click back to it in a second. Based on this velocity and the 700 feet, how long would it take to get there? And then you fit the degradation rate constant to the data. And that's right here. So you plug that in. So you have your data in there, and then you try to change that until it fits pretty good. Do that by trial and error. Then convert that rate constant to a half-life. Our particular concern is a utility trench located at x equals 200 feet out there and y equals 100 feet. What is the concentration there at 10 years? So you can pick that off of 10 years. You can pick that off of, what do we say, y equals 100 and x equals 200 at time of 10 years in there. What is the concentration? Now change it from 10 years from so it's at now, which is 10 years from the beginning of it. Do it 20 years from now, which means 30 years from the start. What is the concentration? And compare it to what you had before. A worker in that trench 1 month after the leak, now so change the time to 30 days and see what the concentration is. Do you suspect it was from the leak? From your plume, is there a high concentration at that point at 30 days? And then just trial and error, play around with the hydraulic conductivity, dispersivity, and see if it has any effect on it. Now we're going to do another model called BioScreen 4. Again, here's a link to get it. It's just a spreadsheet model. And again, if this link is dead, Google it, you can find it. Use most of the same parameters. This one is a little different. You take the kilograms of benzene at the source rather than dimensions of it. And then I'm telling you to use this degradation rate constant. The last one we fit to it, but use this one. And then we're going to model from 0 to 400 feet from the source. So I'll bring up that, and you can see the information here. So see if you can fill all that in. If you have any questions, let me know. Again, I'm putting this out there, and I haven't gotten anyone. I've done the homework myself, but I haven't had anyone submit it yet. So if there are unanswered questions, please let me know. So you run the model, and part A says copy and paste the centerline plot at 10 years. So for 10 years, copy and paste this plot. Part B, copy and paste the plume outlet plot at 10 years. The plume outlet plot at 10 years. So part A is the center line. Part B is the plume. So I go to the plume outlet tab, and I have a 3D plot there, and copy and paste that. Part C, perform calculate animation for the centerline output and look through the time step plots. From the plots and tables, what and where are the maximum concentrations without decay at 5 years and 10 years, and what are the concentrations with decay at the same spot? So walk through that animation. I'll show it to you in a second. And then find where the peak concentration is without decay at 5 years and at 10 years. Make a note of where that is in X position, and then look at the concentration with decay at those X positions and write down that number. Here, I'll show you what I'm talking about. I've run the animation. This is at 10 years. It gives me the concentrations with decay and without decay at a time of 10 years, and then I can scroll back through the animation to the different years and look at the curves and look at the numbers, and I want to make note of that at 5 years and at 10 years. So record those and look at it and see what it tells you. The next problem is at a remediation site. This is a C equals C0 e to the minus KT1. B equals C0 e to the minus KT. We did a problem exactly like this in the notes. It gives you masses at 2 different dates. With then you can get, so this would be, I guess you say mass equals mass 0 e to the minus KT. Gives you for 2 different dates. With that, solve for the degradation rate constant and for the half-life. So remember the T half equals minus log, natural log of 1/2 over K. You can go back and forth between those. It's 213, and the next spring it's 152, so it's not less than half yet, but you should be able to plug in a C over sec 0, so K would equal minus log of M over M0 over the time it takes there. So this is the problem of manipulating the first order reaction rate equation. This one, we have some breakthrough curves, A, B, C, D, E, F, and we have, it's a little confusing because we have letters here and letters there. But see if you can line these up. So there's one more description than there are curves. So see if you can line those. Problem 5 is drawing breakthrough curves. So from these numbers, you should be able to calculate retardation factors for both these chemicals and then plot dispersion low and dispersion high. Don't worry about the exact numbers on dispersion. Do worry about, so you have 4 curves here. So you have C, and your highest is 500 milligrams per liter. This is a plug source or a slug source, so it'll go up and come back down. So your concentration will never quite get that high, but these will have different retardation factors. So you'll have one there, maybe high dispersion and low dispersion. That's not a very good graph. And another one, do give the real numbers for these days here, and then estimate when they'll hit the well. This last one, we know that the chloride, which is non-retarded, non-reactive, it's gone 1,200 meters in 5 years. So that's the seepage velocity or the transport velocity. I'm giving you the answers here. I won't write them all down here, but that's the seepage velocity. And we have the hydraulic gradient. And we know that DMCW has gone 1/3 as far. So obviously has a retardation factor of 3, right? So we have the seepage velocity here we observe from the chloride. We know the DMCW is 1/3 as fast, so calculate that number. Then we know that the V equals K times the change in head over change in distance over the porosity, or if we really want to be rigorous, this is a negative gradient, and we have a negative out here. So from that, solve for, everything else is known, solve for K. And if we have the retardation factor equals 1 plus the bulk density over the porosity times KD, then we can solve for KD, and then we know that KD is calculated from, or estimated from, KOC times FOC. So we should be able to solve for KOC. All right, that concludes the fate and transport section. Next, we'll have some kind of sit back and watch videos on remediation.